Hello everyone. Today we are going to talk about a substitution iterative method with an example. So let's first quickly go through what is substitution iterative method. It is one of the equation that solves recurrences, and it comprises of two steps, that is guess the form and use the mathematical induction to find the constants and show that the solution works. So we are going to we do this work repetitively, hence the term substitution iterative method. We guess it, we substitute it, and then we keep on repeating it, right? So let's quickly move on to the solving of an equation. Let's suppose we have an equation t of n is equal to 2 t n by 2 plus n square, where t of 1 is equal to 4, and we are going to apply a substitution iterative method upon it. So first we just divide our page into two parts, that is the solution part and the expansion part. So starting from the original equation, we replace n, this t of n, we replace the n with n upon 2 and expand it. So when we expand it, we replaced every n with n upon 2, and we get what? Over here we get this n is replaced by n upon 2, and it becomes n upon 2 square. This n is replaced by n upon 2, and it becomes n upon 2 whole square, right? So now we have an expanded equation of t of n by 2, and we can replace this t of n by 2 with this expanded equation, right? So we replace this expansion over here, and then we solved it, and it becomes 2 square t n by 2 square plus 2 n by 2 whole square plus n square. And we are not going to expand right now, we're just going to keep the values in the powers and see what happens. Maybe we come up with a relationship. So moving forward, now we have what? T n upon 2 square. So let's expand this equation. T n upon 2 square we place in the original equation. This n we replace by n upon 2 square. So over here, this n also we replace with n upon 2 square. We get 2t n upon 2 cube, and this n we replace by n upon 2 square. We get n upon 2 square whole square. So again we come back and replace this value, this t n upon 2 square, with the expanded equation, and then we solve it, and we get 2 cube t n upon 2 cube plus 2 square n upon 2 square whole square plus 2 n upon 2 whole square plus n square. Let's do the expansion one more time so that we have a little more understanding about it. So now we replace this n with n upon 2 cube so that we can find out this t n upon 2 cube value. We place this n with, replace this n with n upon 2 cube. Over here we get 2t n upon 2. We just, when you place this n with n upon 2 cube, we get what? N upon 2 4. And when we replace this n with n upon 2 cube, we get n upon 2 cube whole square. So now we place the expanded equation in the original equation, right? Solving it, we get 2 to the power 4 t n upon 2 4 plus 2 cube n upon 2 cube whole square plus 2 square n upon 2 square whole square plus 2 into n upon 2 whole square plus n square. And we expand it, we get what? 2 to the power 4 t n upon 2 4 plus n square upon 2 cube. You can see over here we expanded this part over here, and 2 cube is when we have 2 cube square, we can easily subtract it, and it becomes n square upon 2 cube, right? And from here we get n square upon 2 square. From here we get n square upon 2, and this is simply n square. So this is our expanded form. So what do we do next? We try to find out any relationship that we can find from this equationship. There can be two relationships. One is every step is I. That is, in fourth step it was 2 to the power 4. In third step it was 2 to the power cube. This is one part. The second part, we take common n square, and we get the relationship of 1 upon 8, 1 upon 4, 1 upon 2 plus 1. So if we keep on going, what do we have? We have, for I stages, we have 2 to the power I t n upon 2I. Okay, this is the first part. And secondly, n square will be common, and the relationship will keep on moving as 1 plus 1 upon 2 plus 1 upon 4 plus 1 upon 8 plus 1 upon 16 plus 1 upon 32 and so on, right? So we have two parts. So the first part, 2 to the power I, we know that n upon 2i is equal to 1, so we can by performing mathematically, we can just replace the I with log base 2 n. Okay, since 2 to the power this when we expand it, and we get log base 2 n is equal to I, so we will replace this I and this I with log base 2 n. Similarly, you can see over here, now what happens, the next part, does this make any series, any mathematical series? Yes, it does. It forms the geometric series. It forms a geometric series which can be replaced by which we can be represented and replace this whole series by a divided by 1 minus r, where a is 1 and r is 1 upon 2 in this particular case. Okay, so we now know how to reduce this equation. We place this. Another thing, 2 to the power log base 2 n, when we solve it we can get it n, right? So we replace this 2 to the power log base 2 n with n, as you can see from this solution how it can be replaced, right? And t n upon n, okay, because this part is also n. Then we have n square, and replace this value with the 1 minus 1 upon half, right? So after solving this we get what, t of n is equal to n multiplied by t of 1 plus 2n square, right? So this 2n square, we already know that t to the power 1 is equal to 4, t to the power 1 is equal to 4, so we just replace this value over here, and we get the time complexity equation as t 4 of 4n plus 2n square. From this we can conclude that the big O of n is equal to n square. Hence we can solve this, we have solved this recurrence equation with the given values of 2t n upon 2 plus n square, where t of 1 is equal to 4. So I hope you have a better understanding of substitution iterative method. Kindly subscribe my channel. Thank you very much.